Good morning. Welcome to the Moonshot Go6 International Symposium. For international guests and invited speakers, welcome to very hot and humid Tokyo. I will give an overview of the Moonshot Go6 as a program director. So quantum computers are expected to eventually outperform supercomputers. However, the quantum computers available today cannot perform large-scale quantum computation due to quantum errors. Moonshot Go6 is an ambitious program to overcome quantum errors and realize a fault-tolerant universal quantum computer that will revolutionize economy, industry, and security by 2050. Let me briefly introduce myself. I'm the professor and director of Center for Quantum Information and Quantum Biology, Osaka University. I spent 10 years at NTT research laboratories working on quantum optics and quantum information before joining Osaka. In 1999, I launched the first explicitly quantum computing project in Japan. And I learned a lot from Professor Arthur Eckert and Professor Isaac Chan to do that project. That was about the time the world's first superconducting qubit was demonstrated by Professor Yasunobu Nakamura and Professor Zhou Shen Tsai at the NEC's laboratory in Tsukuba, Japan. After nearly a quarter century, the superconducting quantum computer developed by Professor Nakamura's team at RIKEN is running at Osaka University as well as RIKEN. However, we all know that the error-free large-scale quantum computer is still far away and quite challenging. What is Moonshot program? The Moonshot is a bold new program for creating disruptive innovation decided by plenary session of Council of Science, Technology, and Innovation, CSTI, the Ministry of Education, Culture, Sports, Science, and Technology, next, with funding agencies, including Japan Science and Technology Agency, JST. We tackle the challenges facing future society through ambitious, goal-oriented research projects, leaping beyond the limits of conventional technology without fear of failure. What are the Moonshot goals? The goal 1, overcoming limitations of body, brain, space, and time. Goal 2, ultra-early disease prediction and intervention. The goal 3, coevolution of AI and robots. The goal 4, cool Earth and clean Earth. And goal 5, sustainable food supply and consumption. And the goal 6 is fault-tolerant universal quantum computer. The goal 7, to age 100 without fear of, without health concerns. The goal 8, controlling and modify the weather. And goal 9, increasing peace of mind and vitality. The Moonshot Goal 6 was discussed in the International Symposium on Quantum Technology in Kyoto on 18th December 2019. The Moonshot special session was organized and co-chaired by Professor Yasuhiko Arakawa and myself. We invited Professor Tommaso Carrarco from EU Quantum Flagship and Professor Jacob Taylor and Professor Alexander Cronin from the White House. We aim to realize a society in which science, industry, economy, and security are greatly advanced, and global social issues are solved with the power of quantum computing. As quantum computers can calculate intricately entangled quantum states as they are, it is expected that the accuracy of quantum chemistry calculations will be dramatically improved. As a result, the efficiency of energy and material utilization in industry will improve dramatically, leading to the solution of energy, resource, and environmental problems. For example, the function of enzymes involved in nitrogen fixation and carbon fixation in bacteria and plants will be elucidated. A few percent of entire energy consumption is currently used for the industrial production of ammonia, a raw material for nitrogen fertilizer. If a biological nitrogen fixation by the enzyme nitrogenase is elucidated by quantum chemical calculations on quantum computer and is artificially mimicked, energy saving of orders of magnitude will be realized. Similarly, if we can elucidate and mimic the photosynthesis of plants, we can reduce carbon dioxide and help solve global warming. However, the quantum computers that realized today have only hundreds of qubits and feature very vulnerable to quantum errors and cannot perform large-scale calculations. Quantum chemistry calculations to elucidate nitrogen fixation or photosynthesis require an ideal quantum computer without errors with at least thousands of logical qubits. That is a fault-tolerant quantum computer that performs calculations while correcting quantum errors. To achieve this, it is necessary to significantly increase the number of qubits to provide redundancy, perform quantum error correction, and also lower the error probability below the fault-tolerant threshold. However, the number of qubits can be physically constrained. For example, the number of ions aligned in a trap is limited. The number of superconducting qubits accommodated in a dilution refrigerator is limited. Therefore, it is also necessary to connect multiple quantum computers by quantum communications to operate as a larger scale distributed quantum computer. Since the topology and the strength of the coupling among qubits depend on the physical system, it is necessary to find a suitable quantum error correction scheme and make the fault-tolerant threshold as high as possible. Project managers have been recruited in 3 categories: quantum computer hardware, quantum communications, and fault tolerance. We have adopted 7 project managers in 2020 and additional 5 last year for acceleration. Here are 12 ambitious project managers: 7 quantum computer hardware, superconducting, trapped ion, photon, 2 silicons, 2 neutral atoms, 3 quantum communications, 2 quantum interfaces and networking, 2 fault tolerance projects, theory and software, and development of quantum error correcting system. Dr. Yamamoto Tsuyoshi from NEC is working on development of integration technologies for superconducting qubit, a quantum circuit. Dr. Takahashi Hiroki from Okinawa Institute of Science and Technology Graduate School, a graduate university, is on fault-tolerant quantum computing with photonically interconnected ion traps. Dr. Furusawa Akira from University of Tokyo and RIKEN is on development of large-scale fault-tolerant universal optical quantum computers. Dr. Mizuno Hiroyuki from Hitachi is on large-scale silicon quantum computer. Dr. Tarucha Seigo from RIKEN is on development of scalable silicon quantum computer technology. Dr. Omori Kenji from Institute for Molecular Science is on large-scale and high-coherence Fortran quantum computer with dynamical atom arrays. Dr. Aoki Takao from Waseda University is on large-scale quantum hardware based on nanofiber cavity QED. Dr. Kosaka Hideo from Yokohama National University is on development of quantum interfaces for building quantum computer networks. Dr. Yamamoto Takashi from Osaka University is on quantum cyberspace with networked quantum computer. Dr. Nagayama Shota from Keio University is on scalable and robust integrated quantum communication system. Dr. Kowashi Masato from the University of Tokyo is on research and development of theory and software for Fortran quantum computers. Dr. Kobayashi Kazutoshi from Kyoto Institute of Technology is on development of scalable, highly integrated quantum error correction system. Here is our portfolio. Hardware projects work in competition with each other. Quantum communications project work on quantum interfaces, quantum memories, and quantum communication network for distributed quantum computers. Fortran project work on theory and software for Fortran quantum computers and development of quantum error correction system. Projects in different categories work in collaboration. More than 500 researchers are involved. More than 10 industrial partners, including startups, are involved. The Moonshot Goal 6 is the biggest quantum program in Japan. We have 10 advisors. 3 of them are sub-program directors, and we are expecting 2 more advisors. Some of them chair following sessions. For next 3 days, we have 7 sessions. We have progress reports from 12 project managers and invited lectures from 12 acknowledged researchers from the world. We welcome exciting discussions, hotter than the hottest summer of Tokyo. Thank you for your attention.